Hello everyone, welcome to another video of GPU programming with Mojo. Today we shall learn the design and implementation of a convolution kernel. You might have heard the word convolution with respect to convolution neural networks, where it's primarily used as a feature extraction tool. CNN played a huge role in the AI revolution in the last decade, so it's relevant for us to understand this operation and how it is executed on a GPU. The operation itself is very straightforward. You take a small vector or a matrix and multiply it with a larger vector or matrix. You do an element-wise multiplication and then sum the values. For example, here you multiply k1 with i1, k2 with i2, k3 with i3, and then sum up the values and store it in the resultant vector o1. And you move the small vector one location forward, and now k1, k2, k3 is multiplied with i2, i3, i4 respectively. And then the next step would be to multiply the same with i3, i4, i5 respectively. So it finishes until the last element, which here i6 gets multiplied with k1, k2, k3. So let's see how we can perform the same operation in parallel, leveraging all the parallel architecture of GPUs. The setup for our program would be 2 blocks, 8 threads per block. So in total we have 16 threads. Let's pick 15 elements, and then let's pick a convolution vector, also called as kernel or filter, with size equal to 4. So we have input vector which has 15 elements. We have a convolution vector which has 4 data elements. Let's start by importing the required libraries and initialize the values. We have 8 threads per block. We have convolution size equals 4. We have data size as 15, 2 blocks per thread, and 8 threads per block. Let's start implementing the kernel. We have seen in the earlier videos, we can follow some sort of a blueprint in designing the GPU algorithm. First step would be to get the global index and local index. Next would be to create a shared space for our input vectors. Here it would be a convolution vector of size 4, and then a shared location for our input vector of 15 elements. Since it's split in 2 different blocks, we would say 8 threads per block. So ideally we would have created 8 locations per block, so 16 locations. But the convolution operation on the last element of each block requires 3 extra spaces. So let's look at this visually first as to why it is needed, and then come back to the code. In the GitHub repo, I have included an interactive web page for you to first understand the design visually, and then come back to the code to understand the implementation. So when we see the convolution operation, ideally for any initialization or creation of shared memory, we would have created the 8, in this case as per TPB, 8 threads per block, but we are creating 3 extra spaces. The key insight here is that the last convolution happening on the last element would need 3 extra elements for it to perform the convolution operation and finish and successfully complete it. But we know that shared memory is only visible to threads within a block, meaning T7 does not have access to elements in the other block. So there are elements in the other block initialized, but T7 doesn't have access to this block. So we have to duplicate the data and copy it here as well, so as to finish the convolution. T8 will perform in its own block and finish it, but T7 doesn't have access to it. So since it cannot reach out to block 1, we copy the 9th element, 9th, 10th and 11th element both in block 1 as well as in block 0, just to satisfy T7's operation, which is the convolution operation. Now one might argue that there is duplication of data. Yes, it is a very small price to pay for the parallel performance that the GPU is able to give. So once we do that, we have to we see that we have to initialize 3 extra spaces. but then someone has to copy the data from global memory correctly, or else it will have or yield no value. So we instruct T0, T1 and T2 to copy the values. Now you can ask any three threads in block 0 to copy the 9th, the 10th and the 11th element to help thread 7 to finish its convolution. But algorithmically it's easier to ask 0, 1 and 2 because we can tell thread 0 to copy its first element, which is its own element, jump 8 locations and copy 9th element. We can instruct 2 to do the same, jump 8, copy here. The instruction given to all these three threads would be copy your own element, jump 8 locations and copy the corresponding element from the global memory onto the shared space here defined by 8, 9 and 10. Now the instruction is 8. Do we have the number 8 anywhere? Yes. The threads per block TPB has the value 8. So the instruction can be jump TPB times and copy. Now one has to also note that we have to stop at 3. We cannot ask all these guys to do the same because we only need 3 spaces. Now how do we have the value 3? The convolution size is 4. So we can say convolution vector size minus 1, which is 3. So TPB defines the locations to jump. The convolution size minus 1 tells you how far you should go, and these two will help us design that one extra line where we can instruct only the 3 threads to jump certain locations and copy the thread, which later will help T7, thread 7, to finish its convolution. So that little bit of help is needed to design this algorithm so as to facilitate a successful convolution operation. And this is the insight that you have to derive from this convolution, from this kernel, which is there is a concept of creating extra spaces if we need them. There is a clever way of using some of the threads based on the values we already have initialized, so that we can ask the correct 3 threads in this case to copy the data over. Most of the GPU algorithm design is based on how you prepare the steps. The actual operation is very simple, as you will see. Once you prepare the steps, or once you prepare the memory locations with the right data, then it's a simple dot product where you multiply and produce the output. The actual operation itself is simple multiplication and addition, but the preparatory steps are the ones where we'll have to understand the architecture of GPU and accordingly initialize the data. So then it continues for every element and stores it in the output. While this is happening in block 0, block 1 is also doing the same. So you will see that block 1 is also doing the exact same thing, which also has elements, which also has boundary conditions, which also has extra spaces needed to finish its own set of operations here. If you go back here, you see that there are some extra spaces needed, and the last element of the block 1 also needs some extra spaces to finish its convolution operation. Since this is also the last block, there are only 2 blocks and this is the last block, it doesn't have any elements to copy from the subsequent blocks. So what it does is it initializes the extra spaces to 0. So that's one extra thing you have to keep in mind for the last one. Also, carefully we chose 16 threads and 15 elements. The reason for that is the last thread in the second block, which is essentially our 16th thread, doesn't have any useful operation to perform. If it does, it doesn't crash the program. But as you can see, the value itself is 0 and the convolution when multiplied will yield 0. So cleverly, if you set the boundary condition where perform all the convolution but stop at size, and if you instruct the program to do so, then you can avoid this one extra operation so as to increase your performance gain even more. So these are some of the, this is the design of the kernel. So let's go back to the code quickly and see how it's implemented. So we saw the global index and local index initialized here. We see the shared space being created. The copy operation first would be just to copy over the data from global memory to shared memory. Then we ask threads 0, 1 and 2 from each block to copy over, jump certain locations. That jump is specified by plus TBP, and copy over to its corresponding extra spaces we created. Anything else, if it's the last block, it goes beyond the size, so then initialize that to 0. This is for the convolution vector where there are no such special considerations. You just copy from global memory to shared memory. After any such shared memory activity, always call barrier so that the synchronization of threads are taken place and everything is safe. Then the standard boundary conditions to prevent anything less than size is what we care about, and any threads outside this boundary conditions, it doesn't really matter to us. So we put those conditions in, and we perform. This is your convolution operation. This is the condition which prevents the last convolution, though safe, it's useless because it yields 0. So that's the kernel design and implementation. I hope the visual representation give you an idea as to how to design it, and the code itself is very easy without any pointers or any such boilerplate, so that the design could be implemented pretty easily. And that's one of the aspects of Mojo, where the code looks Pythonic without any complicated C++ templates or pointers. So the design or the algorithm is what you have to worry about, and then the translation to code is pretty straightforward. This block of code helps us executing the kernel. We get the reference to the GPU through device context. We create buffers for output, input, and convolution. We initialize them with values from 0 to 3 and 0 to 7 respectively. And finally, we use the Q function to call the kernel. And our map to host, which essentially we need the CPU to print the output. So we say we let the GPU finish its operation, but then copy over to CPU to print the output that we want to see. So the key takeaways in this video are that you have to recognize that in the convolution operation, the last convolution needs an extra padding. So you need to create extra spaces and copy the correct elements onto that. Once you do that, the operation itself will be successful, but there are certain boundary conditions to be handled, especially on the last block, so as to prevent any useless operations and increasing your performance gain. So I hope this convolution kernel implementation gave you some tips and tricks with respect to designing any GPU algorithm. Thanks for listening to me. See you in the next video.